Okay, welcome everyone for the second talk. The second speaker is Rad Niazadeh, if I pronounce it. Yeah. He is assistant professor of operations management at Chicago Booth. He did his PhD from Cornell in computer science, and he was a postdoc at Stanford as a Motwani fellow, right? And he has won number of prizes at Informs in terms of papers, and also his dissertation won the Revenue and Pricing, Informs Revenue and Pricing Dissertation Award honorable mention. And he works at the intersection of algorithms, learning, and markets. And today he's going to tell us about offline greedy to online.
Thank you so much, Ruta. Hello, everyone. Thanks for coming to my talk, and thanks to the organizers for the great workshop. So today I'm going to talk about how to transform offline greedy algorithms into adversarial online learning algorithms and some of the applications that these techniques have in designing markets, combinatorial optimization, and operations management. So the talk is based on a joint work with Negin, who is sitting in the audience, I believe, and gave a talk this morning. Francesca Suzanne, Joshua Wang, and Ashwin Babandioro. This is almost a finished project, but we have some recent research projects related to this paper. Any feedback still is very welcome. So with no further ado, let me actually jump directly to my talk. There's a lag. All right. Yeah, so this talk is really about platforms that are interacting with different users, and their users arrive over time. And as these users arrive, these platforms should make real-time or sequential operational decisions to optimize their performance and achieve different types of goals. So this type of decision-making has its roots in classic applications, such as airline revenue management, online retailing, and I would say with the advent of online marketplaces, it has found more and exciting applications. So just name a few. I can mention different forms of shared economies, things like ride-sharing, last-mile delivery, online food delivery platforms, or various forms of internet advertising. This clicker is not nice to me. OK. Ranging from a sponsored search, display ad, to video advertising, which is now bringing a lot of new interesting questions to the table, and also cloud computing platforms, which basically is consisting of a market with a cloud provider and a lot of users looking for a storage, virtual machine, et cetera. So I can probably talk about each of these applications for an hour, but I really want to highlight in this talk is that one theme that is kind of common across these applications is a lot of interactions with the platforms and the users, especially in a real-time fashion. So the goal of the platform through these interactions is really learning the behavior of the users and try to optimize these operational decisions to achieve these economical goals. Again. Right. And now, as the platform is trying to do these two basic semantics, it's going to face a couple of challenges. So these are the three that I'm going to focus in this talk. So the first one is the real-time aspect of the decision-making, in the sense that these decisions should be made as the users arrive over time, and therefore the platform should take into account the future uncertainty about the users that they haven't yet arrived. The second one is the non-stationarity of the environment. So I was saying that as the platform is trying to learn the behavior of the users and optimize its decisions, it's going to face three challenges: the real-time aspect of the decision. I was talking about the non-stationarity of the environment, which is really because of the fact that many times user behavior changes over time. And finally, the computational complexity that the platform is going to face simply because of the combinatorial nature of decision-making in many of the applications. And I'm going to get to them in more details. So really, the high-level agenda of this talk is showing you a bag of tools and tricks that can help you to learn and optimize in a computationally efficient fashion in some of these marketplaces, given the three challenges: the real-timeness, non-stationarity, and the combinatorial nature of the decisions. So to make things a little bit more formal, I'm going to focus on these examples throughout the talk: the product ranking problem, assortment planning, and reserve price optimization. Let me tell you a little bit about each of these applications. In the product ranking problem, you should think of a platform that is picking a ranked list of the products to show to the users, maybe shoppers, in order to receive a click. And the goal is to find a ranking that maximizes the probability of receiving a click or maybe user engagement. In assortment planning, I have an offline or online retailer with a bunch of inventories of products that would like to show or display a subset of these products to a customer that is arriving to the store, either the offline store or online store. And the goal is subject to the shelf constraints. I would like to pick an assortment that maximizes some sort of objective. It can be revenue, or it can be market share, AKA the probability of purchase. And finally, reserve price optimization, should think of it as, let's say Google is running a sponsored search platform. Advertisers are there. Search queries arrive. They're bidding for the search query, and Google is running an auction, fixing the auction format, maybe second price auction. The question is, how would you pick personalized reserve prices for these advertisers in order to maximize the revenue? Okay. So in all these three applications, we see the two challenges I mentioned, the real-timeness and time varying. For example, in product ranking, the customer search behaviors are observed online, and they might change because you will have new customers. You might have different sorts of customers. In assortment planning, the demand is revealed in an online fashion. And again, the environment might be non-stationary because of seasonal effects, many other effects that changes the underlying demand, maybe the price sensitivity of the customers, so on and so forth. And in advertising auctions, the search queries are arriving in an online fashion, and the platform is eliciting the advertiser's bids or willingness to pay, again, in an online fashion. And at the same time, these search queries might change, as well as advertisers' willingness to pay because of different reasons. But maybe more important than these two, I want to point out that in these three applications, when you think about the set of decisions that the platform should pick, it's exponential in size of the problem instance. In the sense that for product ranking problem, I have to pick a permutation among exponentially many permutations. In assortment planning, I have to pick a subset. And in reserve price optimization, even if you allow two options for the reserve price of each advertiser, finding the configuration, the vector, you have exponentially many alternatives to try. But not only that you have exponentially many alternatives as a platform to pick, under some mathematical formalizations for these problems, you can establish the NP hardness of finding or solving these optimization problems. All right? So in the rest of the talk, as a running example, I'm going to focus on assortment planning and the easier objective of maximizing market share. This is not the only thing that we cover in the paper. We have a lot of applications. This is really to clarify the techniques and show how we do the type of transformation that I'm going to focus on in this talk. So let me formalize this problem. Imagine we have n products. And my goal as a platform is to show a subset of these products to a customer that arrives. And the customer has some sort of choice behavior. The choice behavior of the customer, I'm going to encode it using this function f of s, which is the probability of purchase, meaning that if I display this set to the customer, what would be the probability that he picks something from this set? Okay? To just drop some of the bells and whistles of this model, I'm just going to focus on this set function. And from now on, because under very natural choice models, this set function is going to be submodular, I'm going to focus on functions f of s that are monotone and submodular. And if you're wondering what are these choice functions, there is a substitution property, which is basically a property that if I show you an extra product, it's going to cannibalize the probability that you pick another product. And under very natural substitution properties, you can show the underlying purchase probability function is going to be monotone and submodular. Okay, so let's say the platform has a very simple shelf constraint, so you don't want to show more than k number of products. Then this problem is just going to be an example of monotone submodular maximization subject to cardinality constraint k. So this is what I'm going to refer as the offline problem. But this is not really the problem I want to solve. In order to capture the online aspect and the non-stationarity of the environment, I'm going to look at the online learning, or better said, adversarial online learning version of the same problem. And what is that problem? I give you capital T number of rounds. At each round, there is a player, an algorithm, that is picking a set of size at most k. And then there is a nature or an adversary that is picking the underlying purchase function, f of t at that time. They play this sequential game together with t rounds. And at the end of each round, the player is going to observe some sort of feedback. It can be full information feedback. In that case, after the interaction, you get to see the underlying function. Or it can be bandit feedback. In that case, you only observe the probability of purchase on the set that you have picked, or maybe just an indicator function whether the purchase happened or not. Okay? So the goal of this algorithm here is to find a sequence of sets, S1 to S capital T, each one with cardinality K, or at most K, so that it maximizes the total probability of purchase over the span of capital T number of rounds. And to just have a benchmark for this problem, I'm going to focus on a very simple benchmark, which is quite common in adversarial online learning. That's the best in hindsight benchmark. What does that mean? I'm going to denote it by opt. Think of the best set that you could pick, best fixed set across all the 2 to the n sets that you have, or n choose k sets that you have. That maximizes basically the value of the total function, the summation of f of t, t from 1 to capital T. So there are some critics around this benchmark. I should say that in adversarial online learning, there are a lot of refinements for this benchmark, as long as you find techniques that can find, or let's say design algorithms that are competitive with respect to this benchmark, then it gives you a pathway to have algorithms that work with the more refined benchmarks. At the same time, if the underlying environment is a stationary or stochastic, then this benchmark with high probability is going to be close to the Bayesian optimal benchmark. So from now on, I'm just going to use this as basically what I'm trying to get close to as much as possible as the algorithm. And here's the catch. Even if you look at the offline problem is NP-hard. So even in the full information version, where you know the underlying function, you won't be able to capture that benchmark. But the good news is in many of these applications, including the one that I showed you, you have access to approximation algorithms. Algorithms such as greedy algorithm, LP relaxation with rounding, or primal dual. We have a lot of experts in the audience that have contributed to this field. And usually the type of guarantee that we have is multiplicative in the sense that we have an algorithm whose, let's say, purchase probability is going to be at least gamma fraction of what the optimum can get. Okay? However, this guarantee only holds in the offline regime and not in the online regime, meaning that if I want to really look at the adversarial online learning problem, this guarantee doesn't carry over to that setting. So what this talk is really about is how we can, basically carry this type of guarantee to the online learning version of the problem. And every time that you hear the word online learning, the 2 words come after that. That's exploration, exploitation. And in this environment where the offline problem is NP-hard, these 2 are going to be also quite difficult. To just give you an idea, what does exploitation really mean? It means that given the historical data, you want to pick the best decision so far. So if the offline problem is NP-hard, probably the extended version, time extended version is going to even be harder. So even exploitation, meaning that finding the best in hindsight optimal or best solution given the historical data, should be a computationally hard problem. At the same time, exploration is going to be tricky because you have usually in these settings, like my running example, you have exponentially many alternatives. And it's not really clear how you can find enough information about these exponentially many alternatives in acceptable time. And now the question is how we can do these things. So what I'm going to do in this talk, rather than trying to attack all approximations of algorithms and trying to transform them into an adversarial online learning version, I'm going to focus on a special class, which is pretty prevalent out there, and that's what I call iterative greedy algorithm. So what you should really think of this class of algorithms are algorithms that they make their final decision in an iterative fashion, where in each iteration you basically solve a local optimization problem. Greedy algorithm is an example. You can think of local search. Most of the first order methods kind of are examples of this class. We have a mathematical formalization for what I really mean by iterative greedy algorithm in the paper. But for the purpose of this talk, think of it as what we know as a greedy algorithm. To give you more concrete example, let's go back to our running example, which is maximizing a monotone submodular function. And probably it's not good idea to explain to this audience that classic result of Nem-Hauser back in 1987, which says a very simple algorithm for maximizing monotone submodular function subject to yes.
78, so it's more classical.
Ah, thank you. Thanks. That's the day I was, or the year I was born, so I should keep that in mind. Yes. Right. So as Chandra correctly mentioned, this is even more classic than that 1978. Nem-Hauser showed us that the greedy algorithm gives you a 1-1 array approximation algorithm for this problem. I want to actually explain this algorithm again with my own language. It's a slightly different language, and the reason is I'm going to build on that language to explain my results in future. So think of it in this way. Imagine that I'm going to start with an empty set to run the greedy algorithm. Now there will be what I call K, capital K number of sub-problems. These sub-problems, you should really think of them as an algorithm that is making a decision. These algorithms are going to interact with each other, communicate with each other, and through this communication, they're going to output a set at the end. So what's the communication protocol they're running? Each sub-problem I minus 1, let's say, is sending a message Si minus 1 to the next subproblem. Now, subproblem I, given the message that it received from the previous one, is going to solve a local optimization, which is finding the best local move. So going back to the algorithm itself, what it really does is that each subproblem I is going to find the next element that if you add it to the set, it maximizes the marginal increase to the value of the function given the message that you have received from the previous subproblem. And these guys talk to each other, return a set at the end, and that would be the final set. Let me introduce a piece of notation. So this delta f si minus 1j is going to be the marginal increase in the value of the function given set si minus 1 when you add element j to the set. So this step can be written down in a slightly fancier version, which is equivalent, and that's the following linear optimization. So what this guy is really doing is picking a point in n-dimensional simplex, a distribution over n alternatives, that maximizes x dot product y, where y is a vector whose jth coordinate is the marginal increase in the function given set s minus 1 when you add element j. Okay? So this is going to be basically a point mass, and then you can sample from this point mass distribution, add the element to the set, and continue. Okay? Cool. So the question is, can we transform an iterative greedy algorithm like the one that I showed you in a computation efficient fashion to an online learning algorithm that has this type of guarantee, approximate regret? Let me spend this slide to tell you a little bit about the guarantee I have in mind. Imagine gamma is the best approximation factor that you can hope for the offline problem. In some sense, for example, let's say getting anything better than gamma is going to be, you cannot hope for a polynomial time algorithm that is better than the gamma approximation. It's gamma APX hard. Then in that case, what I'm going to look at is the following benchmark, is the following guarantee. Gamma regret is defined to be gamma times the hindsight optimal benchmark minus whatever the algorithm gets. So my ideal goal is to design an algorithm such that its gamma regret, where gamma is set appropriately. For example, in the case of monotone submodular maximization, gamma is set to 1 minus 1 over e, to this quantity to be sublinear in T. That's what I'm really trying to target. And we are not the first group of researchers that have thought about this problem. I think this business of trying to reduce the online learning to offline optimization starts from the beautiful work of Kalai and Vempala back in 2005. And there are a lot of interesting follow-ups. The one I want to highlight is the Kakade et al. Paper back in 2009 that shows us that basically for linear optimization, you have access to an approximation algorithm. You can actually transform it into an online learning variant. And not only transform it, it's actually a black box reduction. So without even looking into the algorithm, you can get an adversarial online learning algorithm that carries over the reduction. We diverge from this literature in many different ways. Maybe the most important one is that we look at the case that we have nonlinear rewards. We really do not add any structure on the reward function or anything of that sort. And our main result is basically the following. So we show that if you focus on the class of iterative greedy algorithms, yes, come.
Their algorithm is from 1957.
Right. I mean, they're not looking at submeasure maximization, right? Oh, you mean the year was wrong? I see. I mean, the journal version is 2005.
Yeah, but their algorithm they credit to 1957.
Okay. Right. I trust Kamesh. So, right. So our main result is basically saying that if you focus on the class of iterative greedy algorithms, then there are two natural conditions. I'm going to call them Blackwell locality and robustness to local errors, which will be explained later, that if they're satisfied by the offline greedy algorithm, then you can transform it into a low-regret adversarial online learning algorithm using Blackwell approachability. And the end goal result that you get is basically a square root t regret up to logarithmic factor for full information feedback, and t to the 2/3 regret, again, up to logarithmic factor for bandit information feedback. So there are a lot of things on this slide that I have to decipher, and that's my plan in the rest of the talk. But before that, let me tell you one thing I'm excited about this result, and that's the power of framework. Meaning that what we really do in this paper is we identify some simple conditions that under which you can transform the greedy algorithm into the online learning variant. And then we show a diverse and large class of problems admit iterative greedy algorithms that satisfies those two conditions. And as a result, we can solve a lot of applications in operations management, market design, and combinatorial optimization. And I mentioned 3 of them. There are more. I would be happy to talk about them offline. In the interest of time, I'm just going to focus on my running example. So this is a table in the paper which basically shows that in many different applications, we either get improved regret bounds or we are the first paper that even get any sublinear regret bound for certain categories of problems. And in the rest of the talk, what I'm going to plan is sketching our approach and showing you how we can get this result. So this is the right time for me to pause a little bit and see if you have any questions about the setting, about what I'm going to show, etc. Yes?
So would the result hold if you have like resource constraints?
No. So that's a great question. So this is a type of adversarial online learning that times are not coupled with each other. Even, let's say, bandits with knapsacks in the adversarial setting is actually a hard problem. So I'm avoiding those situations. But this is a great question. So one can think of like assortment planning when you have inventory constraints and try to do the same thing. This is not what we are studying in this paper. But we are considering some variants. I can explain to you later. Yes, Kamesh?
Is there a way of taking continuous greedy and adapting?
Yeah, we have it in the paper. So yes. So most of the first order methods, you can actually transform them from the offline problem to online, including continuous greedy, or better said, Frank-Wolf, essentially. Cool. Any other questions? I think the reason that Kamesh mentioned is if you think about monotone submodular maximization subject to matroid constraint, then the naive greedy algorithm I showed you is only giving you a half approximation, not a 1-1 approximation. But then there is a continuous optimization problem. Once you solve that, thanks to Chandra, we know how to round it into base of a matroid and get the 1-1/e. Pipage rounding is oblivious to the choice of the function. So you really don't need to know the function to do the pipage rounding. As long as you can transform the continuous greedy from offline problem to online problem, then the transformation exists, and we do that in the paper. All right. So let's revisit the Nemhauser's greedy algorithm again. Just as a recap, we have this case of problems. They're going to communicate with each other and output a set. Each one is solving a local optimization problem. Now, suppose I look at the adversarial online learning version. I have capital T number of rounds. At each round, you need to basically let these case of problems to communicate with each other, output the sets. So I'm going to have my case of problems in round 1. They're going to communicate with each other, output the set. Then I go to round 2. Again, the same thing happens over and over. Now, suppose at time t, magically, subproblem I could do its job perfectly, meaning that it could find the next element that has the maximum marginal increase to the value of the function. If this is true, then you can get zero regret. Basically, the approximation ratio is going to be preserved. And the result I showed you is going to be achieved, even a stronger version of that. But obviously, this is too good to be true, because in order for this subproblem at time t to make its right decision, you need to know the function f. OK, so this seems to be too good to be true. But now let's focus on subproblem I. And imagine that rather than this subproblem is making the right decision at every single point of time, it actually makes almost correct decision on an average sense over time. So what I really mean by that is that if I look at this subproblem I that is making decisions across time, suppose this subproblem could make almost locally best moves on an average sense over time. Could I now show that the final algorithm in which you run an algorithm for each subproblem that satisfies that type of guarantee, and these subproblems again communicate to each other exactly in the same way that they were communicating in the offline problem? Could I show that if I put these pieces together, then I can get a final regret? So in order to follow this kind of line of attack, I need to answer two questions. So the first question is the following: how to formally define this notion of almost locally best on an average sense over time? And second is, once I formalize this definition, how can I actually generate an algorithm that gives me, or design an algorithm that gives me this sequence of moves as each subproblem? And the answer to both of these questions is basically at the heart of our reduction, and that's the Blackwell approachability. So what we really use is this assumption, Blackwell locality. So what does that mean? So if an iterative greedy algorithm satisfies Blackwell locality, it simply means that the local move of each iteration can be cast as an instance of what I call a Blackwell game. And once that can be done, then you can use Blackwell approachability in order to do the task of that subproblem. So I'm going to explain this more. This is high level what's going to happen. So now that I kind of know what I should do for each subproblem, how to put the pieces together and prove the final result, it turns out that what we really need is some sort of robustness to local errors. So what does that mean? Offline robustness means that if I run a greedy algorithm, for example, and then at each iteration I'm making a small mistake, then this mistake should bite me only as much as the mistake itself at the end. There should be no error amplification. And then extended robustness means that now suppose I have a time-extended version of the same problem. If I'm making mistakes that on average over time, they are small, it should again bite me as much as the error itself, and there should be no error amplification. So as long as these conditions are satisfied, then you can glue the pieces together with the guarantee of the Blackwell approachability, which I'm going to explain later. You can get the final result. But the good news is I actually don't know any iterative greedy algorithm in the context that I care about that they violate this extended robustness property. So this is kind of a very universally satisfied condition. And Blackwell approachability, I'm going to show you, is a very rich setting, so it can capture so many different problems. And this is why we could design so many online learning algorithms for different problems. All right, so this is going to be a mini lecture on Blackwell approachability. And after that, I'm going to tell you how you can transform the Nemhauser et al. Algorithm into the online learning algorithm using Blackwell approachability. Hopefully, by the end of this part, I can convince you something interesting is happening in this paper. So what is the Blackwell approachability? So a Blackwell game is basically a two-player game, two-player zero-sum game between two players. Player one, I'm going to refer to it as algorithm, and player two, I'm going to refer to sometimes as adversary. Player one is picking a strategy X from curly X, and player two is picking Y from curly Y. The game is endowed with a vector payoff that maps the pair of strategies of the algorithm and adversary into a d-dimensional vector. This vector payoff should be bi-affine, meaning that with respect to each of its inputs should be a linear function. The game is also endowed with a convex compact set known as a target set. And the way that the game is defined is the following. These two players play simultaneously, X and Y, are their strategies. The goal of players 1 is to land in the target set S. Basically, R should be in S. That's what the player 1 is looking for. And player 2's goal is that the vector payoff should not land in the target set S. A Blackwell sequential game is a repeated version of the same game where the two players are going to play repeatedly. Player 1 is going to play a strategy XT. Player 2 is going to pick a strategy YT. And this time, the goal of player 1 is trying to approach the target set, meaning that it wants to pick a sequence of strategies, X1 to X capital T, such that no matter what the player 2 does, the average vector payoff gets closer and closer to target set S. So let me formalize this. We say a target set S is GT approachable if player 1 has really an adaptive strategy that can generate a sequence X1 to X capital T, such that for any sequence Y1 to Y capital T, the distance of the average vector payoff and target set S is at most GT. And you should really think of GT as a little O1 that converges to 0 as T goes to infinity. So different norms can be used in this distance function. And because of that, you might need different algorithms. In the classic work of David Blackwell back in 1956, I'm pretty sure this one is 1956. In the classic work of David Blackwell, they considered L2. But for reasons that I would be happy to talk about it offline, we actually need infinity norm in this paper.
So it doesn't have anything to do with multiplicative?
Great. Further developments show intimate connections to online linear optimization and online convex optimization. So multiplicative weight update is a form of online mirror descent, which is an algorithm for online convex optimization. So there is actually complex reduction that reduces Blackwell approachability to either online convex optimization and online linear optimization. There are different reductions. The other way is easy, meaning that if you have an algorithm for these two guys, you can easily get an algorithm for Blackwell approachability, but the other way is a little bit more complicated. But in some sense, mathematically speaking, this problem is equivalent to adversarial online learning for linear objectives or convex objectives. But the reduction is so complex that you can't see the underlying online linear optimization when you look at a Blackwell sequential game. All right, so now here's one question. So what would be a condition on the set S and the other semantics of the game that guarantees this game is approachable?
Just to clarify.
Yes.
So X1 to X3 are oblivious of Y1 to Y2, like, because they are picked upfront.
Y1 to YT, you mean? Good. In the Blackwell's paper, he thinks about oblivious adversaries. But then there are further developments that actually can get guaranteed against adaptive adversary, almighty adversary, that looks at the previous strategies of the algorithm and adaptively changes Y. And in this paper, we are fine with adaptive adversaries. All right. So the question is, when we can say that convex set S is approachable? So here is the guarantee. A convex set S is satisfiable if such a very strong guarantee holds, which basically means that player 1 has a globally good strategy. As player 1, I have a strategy X that no matter what player 2 does, the vector payoff is going to land in set S. So this seems to be a very strong guarantee. Let me introduce a weaker notion. So a convex set S is called response satisfiable if as player 1, I always have a good best response against player 2, meaning that whatever player 2 does, I have always a strategy X such that the vector payoff lands in the target set S. And finally, let me show you another requirement, which is somewhere in between. So we say a set S is half a space satisfiable if for every half a space that contains S, it is satisfiable, the first one. So this tree seems to be related, but it's not really clear which one is the stronger. I mean, definitely this is the stronger, but it's not clear which one between the two is stronger, which one is not. So here's the beautiful result of David Blackwell. Convex set S is approachable if and only if S is response satisfiable. And not only that, you can actually show that the response satisfiability and half-space satisfiability are actually equivalent conditions. And this further development, which is the connection of Blackwell approachability to online linear optimization, online convex optimization, basically shows that not only you get approachability result, but also you can get the g of t, which is order 1 over square root t. And the algorithm is going to be computationally efficient as long as you have access to a separation oracle for the convex set S. Okay. So kind of a technical note, as I mentioned earlier in the paper, we need L infinity distance guarantees in the approachability. This makes the underlying algorithm a little bit complicated. It turned out that all we need to do is running a follow the regularized leader that its regularizer is strongly convex in L1 norm everywhere, not only on the positive side. And this was kind of like a cute algorithm that we had in this paper. Maybe it will be of independent interest for other purposes, just wanted to point it out. So from now on, you can assume that Blackwell approachability, as long as the conditions on this slide are satisfied, has an algorithm no matter whether you have L infinity distance or L2 distance or even L1 distance. Okay? So let's go back to Blackwell locality condition, Nemhauser's greedy algorithm. So we say an iterative greedy algorithm satisfies Blackwell locality if the optimization step of each subproblem can be cast as an instance of Blackwell game. So this is basically a reduction. So I have to introduce gadgets that can interpret the task of the subproblem as an instance of Blackwell game. Instance of Blackwell game consists of 2 players, bi-affine vector payoff, and a target set S. So basically, I have to show you how to pick a player 1's action. So in this case, player 1 action is really going to be finding the point ZI. Player 2's strategy, how is it related to the task that this subproblem should do? What is the bi-affine vector? What is the target set? And once I defined all these gadgets, I'm hoping that I satisfy this condition, meaning that if the reward function is in S, it should be if and only if with the ZI being the best local move. So if I can introduce these gadgets that satisfy this condition, then I say the algorithm satisfies Blackwell locality, and then basically I can cast it as an instance of a Blackwell game. Cool. So let's see why this is a Blackwell game. It's very simple. Player 1 is picking a distribution over n elements. So I set curly X to be n-dimensional simplex. Player 2 is going to pick a vector Y, where the jth coordinate of the vector is just the marginal increase in the value of the function. Now I can define a bi-affine vector payoff, R, where its jth coordinate is x dot product Y minus Yj. So this is bi-affine. And my target set is going to be positive orthents, as simple as this. Now here's the funny observation. If R, X, and Y is in S, then this basically means that X dot Y is greater or equal than Yj for every J. That means X dot Y is going to be the argmax. Basically, it's going to be the maximum Yj. So this is how you can implement the max function using Blackwell game. But not only that, many complex local moves can be cast as a Blackwell game. All right. So let's put all the pieces together. Once you cast the task of each subproblem as a Blackwell game, you can run k parallel instances of the Blackwell approachability algorithms for these subproblems. The Blackwell algorithm 1 is going to take care of the task of subproblem 1. Blackwell algorithm 2 is going to take care of task of subproblem 2, so on and so forth. In each time, they're going to communicate exactly in the same way that in the offline algorithm they're going to communicate. And then they return a solution, in this case, a set of coordinated k, that basically is going to be the final set that you output at each round. I'm swiping some of the details under the rug. Maybe the most important one is that after you're finished with a round, you have to give proper feedback to each of these Blackwell algorithms, because at the end of the day, they're online learning algorithms for the Blackwell approachability problem. So you need to be able to create the vector payoff, which is the actual feedback that the Blackwell algorithm needs in a computationally efficient fashion. Once you can have that vector payoff, you can give it back to each Blackwell algorithm, and in this way, they're going to finish their operation. Yes, Kamesh?
Is this as efficient as the algorithm, or is this involved in complex
Not really. I mean, it's almost as efficient as the greedy algorithm. As long as, so what is the task of the Blackwell approachability algorithm? It's just like solving a one optimization at that step. So assuming that you can do that optimization by just like one call to some optimization oracle, then it is as efficient as the greedy algorithm. But what is that optimization problem? Follow the regularity there, you have to be able to find the regularity there given the historical data, right? So that's the extra thing that you have to do in each step.
What is the, for the simple case of cardinality constraint?
Right.
What is the algorithm?
Oh, so the algorithm is basically, there is one online learning algorithm sitting at position 0, which is picking the first element. There is another online learning algorithm picking the second element. There is another one picking the third element. So there are k online learning algorithms that in parallel are running and picking the elements. So online algorithms 1 to I minus 1 at each time, they come up with a set of size cardinality I minus 1. They send it to the other online learning algorithm. That guy is going to pick the next element. And in fact, at that round, you don't know the function. So this communication is going to be used in order to create the feedback that each online learning algorithm needs in order to update its weights or whatever. For example, if it's like using multiplicative weight update, you have to give the feedback so that the weights get updated. Yeah. Yes?
Does any of your analysis use the
We do use that, yes. So basically, our algorithm is going to rely on half-space satisfiability. Because half-space satisfiability gives you a natural oracle. For each half-space, there is one globally good strategy you can play. So this kind of suggests a natural algorithm, which is like finding a right half-space and then playing the strategy corresponding to that half-space if it is half-space satisfiable. So we build on top of that and get the final result. Yes? Yeah, so in local search, you don't solve an optimization problem. You just like, I mean, it's kind of like a local move. So all you need to do is, you should tell me what local search you have in mind, and I try to cast its local movement as an instance of a Blackwell game, which means I have to find a target set, a bi-affine vector, and two players that play that. Like, for example, local search for maximizing submeasure function, you can easily do that. So just, I mean, I can tell you the details if you want, but there is a reduction that can take care of that. Another example I can mention is maximizing non-monotone submeasure functions, right? So there, in fact, at each iteration, you have to solve a saddle point optimization. It's not really a maximization problem. And again, there is a way that you can cast it as an instance of a Blackwell game. So we have done all of that in the paper. All right, so the final step is the actual proof, and the proof is really not that difficult once you have all the pieces. You basically need to glue the guarantee of the Blackwell approachability with the robustness to local errors, the time extended version, and that gives you the final regret bound. All right, so we also studied the bandit version. We solved the bandit version. For that, you need to introduce a new variant of the Blackwell approachability, which we call bandit Blackwell approachability, and design an algorithm for that. There is a new tool that we need in this case, which is trying to come up with an unbiased estimator for the vector payoff of each of these Blackwell algorithms. So that requires designing what we call the sampling device in the paper. And the rest is pretty much the same technology that we had before. In the interest of time, let me actually just quickly show you some of the simulation results we have. We ran our algorithm for product ranking and reserve price optimization on synthetic data. As it turned out, that the algorithm can actually pick up the pattern in the data pretty well. So our benchmark, which is the best in hindsight benchmark, is pretty weak, but the algorithm is not as weak as the benchmark. This is why you see negative regret in this slide for both the full information and the bandit information. This is for product ranking. And then we observe exactly the same type of results in the reserve price optimization problem, which is kind of an indicator that the benchmark is not a very strong benchmark when there is a structure in the input instance, but still the algorithm can pick up the pattern very well. So let me try to conclude my talk. What we saw was basically how you can transform a class of greedy algorithms into their adversarial online learning variant using Blackwell approachability. And the final result was getting a square root T regret with full information and T to the 2-third regret with bandit information. There are several different problems and applications that we study in the paper. I'm going to be around, would be happy to talk about any of them with you offline. But it's kind of a large set, and I'm happy to hear your thoughts if you have any suggestions for another application that we can add to our framework. So with that, I want to conclude my talk. Thanks a lot for your attention. All right. Yes.
So you said that for bandit you get T raised to 2/3. I mean, is there a lower bound saying you can't get square root T, or is it like?
Great question. We don't have a formal lower bound, but let me tell you why I think actually T to the 2/3 is best possible. So you kind of need to create the feedback that each Blackwell algorithm requires in order to be able to run this strategy, right? Here's the thing. You're solving a submeasure maximization problem, for example. And then the vector payoff of each Blackwell algorithm is totally different from another Blackwell algorithm. Mm-hmm. So the only way I can have an exploration round that is meaningful is targeting one of these Blackwell algorithms and basically focusing on that round, trying to design a set that gives me the proper unbiased estimator for estimating the vector payoff of one of these Blackwell algorithms. So in short, what I'm trying to say is that you need to waste a round in order to give any meaningful feedback for one of these algorithms, one of these Blackwell algorithms. And in that round, there is really no guarantee on how much you can get the final reward. Like, for example, in the submeasure maximization, let's say for one of these subproblems, I know that the previous set was some particular set Si-1. Now I want to see how much extra gain I gave by adding different elements. So the set Si-1 union J, well, so this might be very far from the optimal set. But in order to create a feedback that this Blackwell algorithm requires, you need to kind of like waste that round to just, output a set which is Si-1 union some random element and then try to use importance sampling to find the unbiased estimator. And in online learning, if exploration costs you one round, then you cannot do better on T to the 2/3. This is information theoretically tight.
What is the dependence of the regret on other parameters besides T? Like
Great
specifically
question.
K, yeah.
Great question. Linear in K, as you probably expect. So the robustness to local error says that the error is not going to be amplified, but it's going to bite you as much as the error itself. Meaning that if I have epsilon error in one of the rounds of the greedy algorithm, at the end I'm going to have K times epsilon in my final additive error. And this K times epsilon will be translated to K times the square root T regret. The best information theoretic lower bound that exists for the monotone submeasure maximization in particular is actually K square root T. So there we are tight, but we have some other applications where our dependency on the number of subproblems is not optimal. Yes? Yeah.
Is this like because you're doing this because of this parameter K, like, do you observe the same thing for standard multi-arm bandits, or like or is this?
Yeah.
My question is, is there a different benchmark that can be used if?
Great. Yeah. We didn't try different benchmarks, but definitely you can think of some refinements. For example, there is this random restart benchmark, which with some frequency is going to restart the hindsight optimal. I don't recall if we ran any experiments with respect to those benchmarks. Maybe Nagin remembers something. No, but no, this is a great suggestion. I think we should think of that.
Yeah, as a benchmark, we compare it to the greedy algorithm, but.
Right. That's the half times the.
Yeah.
Nagin's point is, the baseline for the
theoretical
regret
result.
is really not half times the optimal offline, because in these applications, it's hard to find the optimal offline. So we compared with the greedy. But even with respect to greedy, which probably is better than half times opt, we have negative regrets. So I think this is good news for us, but I don't know how to explain it.